So in section 2.2, we looked at finding complete graphs. So we did a rent-a-car problem last week where we looked at finding a complete graph. And remember that sometimes finding a complete graph means narrowing the window down to values that make sense for a word problem. So for example, if x-axis represented time, it might not make sense to let the x-axis go negative, because negative time, that doesn't make sense. All right, so keep that in mind when you are finding a complete graph. So we're going to start off by looking at an example of a company that has two types of costs: fixed costs and variable costs. The difference is a fixed cost stays the same, and a variable cost will change depending on this company is going to produce something. The variable cost will change depending on how many of the thing we produce. So this company has a fixed cost of $200,000. So maybe that was the cost to buy the equipment. Once they own the equipment, it doesn't matter how much they use it. They paid $200,000, now they own it. So that's the fixed cost. But there's a variable cost of $1.50 per shirt. So obviously, the more shirts they make, the more it costs, because maybe they have to print ink on the shirt, and they have to buy a blank t-shirt. So it costs them money for each shirt that they use, that they produce. So they make the shirt for $1.50, they sell the shirt for $4. And the three things we're really going to look at here are profit. When do you start making money? So we're going to be looking at a break-even point. So we're going to talk about that too. So I want to find a graph that represents cost, and then I want to do a separate graph that represents revenue. So cost, revenue, and profit are three different things. Cost is what the company pays to make their product. Revenue is all the money they take in, and profit is the difference between the two. So let's start with costs. Well, first thing we need is a variable that represents the amount of t-shirts that we produce. So how about, Layla, what do you want to use for a variable that represents the amount of t-shirts that this company makes? T, okay? So we're going to use T. So we're going to write the cost as a function of the number of t-shirts. Okay, Caleb, you think you could give me a formula for my cost that represents the fixed cost and the variable cost? And what's the variable we're using? T. Yep, so 1.5 T plus 200,000. Good. There is an equation for the cost. And we're going to do revenue the same way. What would be an equation for my revenue? Not necessarily my profit, just the revenue. It's just the money that I take in. Yeah? 2.5T. Let's see. So what do we sell each shirt for?
$4.
$4.
Oh. Okay.
So the revenue would be 4T.
Is that it? Okay.
Yep. Now they want graphs. What kind of values for T wouldn't make sense in the situation? Negatives. So on the calculator, let's go ahead and put that in. So you can put the cost or the revenue in Y1 or Y2, it doesn't matter. Just put 1.5x plus 200,000 and 4x. So those should be your two equations. Okay, so I agree with you, negatives don't make sense. So I'm going to put my x min at 0. X max is the number of t-shirts we produce. I don't know. I have no idea how many we're going to produce. Let's say we produce up to 10,000. What we're going to be looking for is a break-even point. If we can't see that on the screen, we might need to set that higher. Now, Y min represents a dollar amount. What kind of dollar amounts don't make sense here? Negative. You can't have negative cost and you can't have negative revenue. When you subtract the two, you could have negative profit. But you're not going to have negative revenue or negative cost. So 0 is good. How about Y max? What should we go at least up to?
Is profit the absolute value of C minus R? That's what
Profit, you wouldn't need
Oh, yeah.
Yeah, you don't want to do absolute value because you do want to reflect if it's negative. That means you lost money.
Alright, which one do you subtract from?
We're going to do that in a minute.
Okay.
So that'll be the next thing.
Okay.
But what should my Y max be? Yep.
A little over 200,000.
Yeah, we need to go over 200,000 because our cost has a y-intercept of 200,000. So I would probably even do, now let's just try 250. Let's hit graph and see what it looks like.
Oh.
There's our costs and there's our revenue. So it's kind of hard to tell, but the red line is steeper.
Yeah.
It has a slope of 4. So it's going to catch up, but not if you only sell 10,000 shirts. So let's set that a lot higher. Let's try like 100,000 shirts. So we can see our cost better. We can see our revenue.
Oh, I just couldn't see my cost. Did you change the X as well?
Yep.
Oh, okay.
But what do I need to change now? Yeah, I'm trying to think where these are going to cross. So I would definitely change the Y max. Let's try 350,000. I think that's going to get us pretty close.
Oh,
So there's our cost, there's our revenue. Yeah, we got it. And that's a complete graph of this problem. So when they ask you for a complete graph, what do you need to write down? The window. There's your window.
Is that for costs? Oh, wait, is that multiple? Yeah.
So I'm looking for these two. And those two. And there might be more than one. I mean, if you did X at 150,000, that's probably fine. If you put your cost at 400,000, that's fine. But the important thing we want to be able to see is where they cross. Because once your expenses are equal to the amount of money that you've made, then you've broke even. So the break-even point is when cost equals revenue. That's the formula for the break-even. You set the costs equal to your revenue. And essentially what that means is you are at $0 of profit. You haven't made money, you haven't lost money. So I already answered that. But for a graph, when you graph cost and revenue, where would the break-even point be? The intersection. Yep. So it's the intersection of the cost and the revenue graphs. And we're going to find what that is. Okay, we'll do it algebraically, and then we'll do it graphically. Well, to do it algebraically, you just do this. Literally, look what our formula was for C of t. Look what it was for R of t. And substitute in those two things and solve. So C of t, what was the cost to make each shirt? 1.5. And the fixed cost were how much? 200,000. So there's your cost. And the revenue was how much per shirt? 4. Okay, so solve for t. So we're going to end up with 200,000 equals 2.5t, and divide by each side by 2.5. I think that's 80,000. Is that 80? Okay. So that's 80,000 shirts. That's the number of shirts that the company must sell to break even. Any questions on how we solve that algebraically?
Okay, so that makes sense.
So now let's do it a different way. We'll do it graphically. So the first step to do it graphically would be to type your equations in y1 and y2 and set your window. Once I do that, I got my graph. Does anybody remember what we pressed to find where they cross? Nate?
Second calc and then 5 for intersect.
Second calc, and then 5 for intersect. Alright, so does everyone have the algebraic way? Okay. Let's go with this. So it asks me for first curve. What do I do when it says first curve? Yep, make sure it's on the blue one, hit enter. Okay, now it says second curve. What do I do? Yeah, make sure it's on the other one, hit enter. And the last thing it's asking me for is the guess. You can really just hit enter because this isn't like a parabola and a line that could cross twice. They're only going to cross once, it'll find it. And that's what we get. So 80,000 shirts. If you sell 80,000 shirts, looking at that graph, how much will it cost you to make 80,000 shirts? John? 320,000. If you make 80,000 shirts, it will cost you $320,000. What will be your revenue if you sell 80,000 shirts? 320,000. It'll be exactly the same. Okay, so this is your costs, and the red one was your revenue. Any questions on solving that graphically? Okay. So that was all that was really left in 2.2. That was it. All right, so 2.3. Solving linear and quadratic equations algebraically. So remember first what an equation is. An equation is when you put an equal sign between two expressions. If the equation uses the variable x, then we would say you have an equation in x. If, like the last problem, we use the variable t, you could say you have an equation in t. It means it uses the letter t. Whenever you're graphing on the calculator, you do always have to use x for the variable when you're at y, when you're using the y equals screen. You can't put in a different button.
Can I ask a question just out of curiosity? The other variables on the calculator are like a capital T and lowercase n. Both of those we use for.
When we do parametric and polar graphing. Specifically the capital T for parametric and the theta, Greek letter theta for polar. That's chapter 9, so we're a little ways away. So solve an equation. What does that mean? It means find all the values for x that make it true. For linear equations, you generally have three cases. No solution, infinite solutions, or one solution. Linear, imagine two lines. Think of the three things that could happen when you draw it. If the two lines you draw are parallel, they never cross, no solution. If they have different slopes, then they're going to cross somewhere because they're not at the same angle, so they're going to cross. Or if they have the same slope and the same y-intercept, then they're parallel, which essentially means you're solving the same equation. So it's an infinite amount of solutions. That's the three things that can happen with linear. Now with quadratic, you think of like a parabola, and think of how many times a parabola could cross the x-axis. 0, 1, or 2. So this case right here, where you graph two lines and they come out exactly the same, that's called an identity. An example of an identity would be something like this. If you solve that, you're going to end up with 4 equals 4 on both sides. This is 2x plus 4. This is 2x plus 4 on the right. They're exactly the same thing. So that equation is an identity. It has an infinite amount of answers. Here's another example of an equation that's an identity. 3x plus 2 is what you have on the left. And if you simplify the right, you have 3x plus 2 on the right. Same thing on both sides. So the solution there is all real numbers. Any questions on that? Yes?
Wouldn't that be wrong? Because wouldn't it be 3x plus 3? Or would you...
Oh, it's the minus 1.
Oh.
Yeah.
Now, the other type of equation we can have, which this is what happens most of the time, is it's not an identity, but it's a conditional equation. So in a conditional equation, it's an equation that could be true if x meets the right condition. So in this case, if x equals 5, then it is true. But it's certainly not an identity because you can't fill in anything for x and have it be true. There is a specific value. So conditional equation that's linear has one solution.
Isn't that just the same as the equation with one solution?
Yeah, an equation with one solution, yeah, would be called a conditional equation.
Okay.
Yeah. Same thing when we get to quadratics, but with quadratics, a conditional equation can have two solutions because it's quadratic.
Oh, yeah.
Linear conditional equation only has one. So to check that a number is a solution to an equation, we plug it in and see if we get a true statement. Now, at this point, most people in here probably wouldn't know how to solve this. X cubed minus x plus 6 equals 0.
Would or wouldn't?
I don't think they would. What makes that hard to solve?
There's two different variables for x. Well, they're not the same.
Well,
I don't know how to say it.
I would argue that if you had two different things like that, everybody in here could solve that one. Because it's cubed. Right? That cubed really complicates it. So the fact that you have cubed and the fact that you have minus x, that's the problem. If all you had was cubed, something like this, like x cubed equals 8, well, that's easy. The answer is just 2.
Yeah.
But you didn't have x cubed plus x or minus x. That starts to complicate it. So in this one, I don't want you to solve it. I'm going to tell you that negative 2 is a solution, and I just want to verify. Now, if this is true, -2 is an integer. If the answer to a cubic equation is an integer, then there is probably a way you can solve it pretty easily. There's a way to do it. If this came out to like an irrational number, and then it's going to be a little harder to figure out. Okay, so how do I check that -2 is a solution to that equation? Yeah.
You just plug in -2 for x.
Yep. And my suggestion would be when you do that, make sure you put anything that had a variable in parentheses. That's important if you want to type it in on the calculator as well. But I don't think we'll use the calculator. I'm going to put a question mark there because I don't know if it equals 0. That's the hope. And -2 cubed gives me how much? -8. Minus a minus is going to become a plus. -8 plus 2 gives me?
-6.
And -6 plus 6 is 0. So when I plug the number back in, I ended up with a true statement. 0 equals 0. That means -2 is a solution. Doesn't mean it's the only solution, but it at least is one solution. Questions on that? Okay. So, linear equations. So in a linear equation, it has the form, or it can be rearranged to have the form, ax plus b equals 0.
So linear equation in x at the top.
Yep. Now, to be a linear equation, a and b can be any real number that you want, except a can't be 0. Because if you make a 0, then you've wiped out that part, and all you have now is a number equals 0. Okay, that would not be considered a linear equation.
But I think I left my Chromebook in here.
Yeah, you can double check. Go ahead. See if it's third C, right? Yeah.
Oh wait, let's say ax.
Yeah.
Have a nice day.
Yep, you too. So again, a and b can be any numbers, any real numbers that you want, except a cannot be 0. So we're not going to spend a lot of time on solving a linear equation. Just jump right into one and solve it. So we've got 2 and then in parentheses 2x minus 3 plus 3 in parentheses x plus 1 equals 5x plus 2. All right. How about Jess? What would be my first step to solve that?
Distribute
Okay, distribute what?
the 2 to the ones in the parentheses, and then you can do the 3 to the ones in its parentheses.
Yep. So if you do out all of that distributive property, can you tell me what you get?
4x minus 6 plus 3x plus 3 equals 5x plus 2.
Okay. So we got 4x minus 6. That's your first distributive property. 3x plus 3 is the second one. And then the 5x plus 2. If I combine everything on the left, how about Christian? What would I get when I combine all that?
7x plus or minus
7x minus 3 equals 5x plus 2. So bring the 5x to the other side. Add the 3 to the other side. When we subtract 5x from both sides, we get 2x on the left. When we add 3 to both sides, we get 5 on the right. And we're done. So x is 5 halves, or 2.5. Any question on solving? Okay. Basic, very quick review of a linear equation. Now, you might say, well, wait a minute, that's not in the form, wherever I wrote it, ax plus b equals 0. Well, it could be if I took this last step, 2x minus 5 equals 0. There it is. So I can eventually take the equation they give me and write it in that form. If you can do that, it means it's linear. All right, absolute value. So when we want to solve an absolute value equation, what the goal here is you take and you split it into two problems. When we split it into two, the first problem is exactly the same as the original problem we had, except we take away the absolute value bars. So if you think about like a simple one, x plus 2 equals 5. In order for that to find what works for x, what's inside here could come out to two different values and it would be okay. What's one value that x plus 2 could come out to and it would work? Yeah? What is it?
3.
Not x, just x plus 2. What could x plus 2 equal, Ben?
Could be -5.
X plus 2 could equal -5, and that would work. Or, what else? Or 5. If x plus 2 comes out to +5 or -5, we're going to be okay. So that's why I said to split it into two problems, take the original and get rid of the bars. That gives you the first one. The second equation is the same as the original. We take away the bars, but we make the number on the other side a negative. And that's your second equation. So either what's inside the bars equals the number you have on the right, or what's inside the bars equals the opposite of the number you have on the right. Either way, it'll work. Now, I didn't do this in this problem, but before you solve it, you do have to make sure that the absolute value is by itself. And I'll write that in as we solve this problem. So check to make sure the absolute value expression is isolated. What that means is you don't want to have something like this. That's no good. You don't want to have addition or subtraction outside the bars. You also wouldn't want to have something like multiplication. So your first step is to isolate the absolute value expression. If that was my problem, I would divide each side by 2 to start. If that was my problem, I would subtract 2 from both sides. Don't worry about what's inside here. Just worry if there's anything outside the absolute value, and get the absolute value by itself first. In this one, it already is. So any questions on what I mean by that?
Wait, sorry, what was the original one?
Right there. So let's split it up. Either 2x plus 3 could equal 5, or 2x plus 3 could equal -5. And solve each equation. So you're going to get 2x equals 2, x equals 1, or 2x equals -8, x equals -4. That's it. That's how you solve an absolute value equation.
Oh, I remember.
Now, what would you do if this was your problem? We're not going to do this, but what if you had 3x plus 10 equals -6? What would be your first step? Yeah?
But it's the same thing. You just have to split it, right? It's two different things. Or one is the negative value and the other is a positive value.
Okay, so you could split it and solve it and do all that work. But what's going to happen here?
It's not gonna work because an absolute value can be negative.
You can never take the absolute value of something and have it equal a negative number. So if you split this problem up and solve it, you will get two answers. But they won't work because you cannot take the absolute value and have it equal to a negative. But what if you had something like this? Negative 10 plus the absolute value of 3x plus 10 equals negative 6. What would be your first step here? Yep. Right. You would add 10 on both sides, and then once you do that, you're fine. So don't look at the right-hand side and say, oh, it's negative, I can't do it. Is the absolute value isolated and it's equal to a negative? Okay, then you can't do it. But if the absolute value isn't isolated, maybe when you isolate it, it'll turn into a problem that you could do. Any questions on that? Okay. All right, so mixture problem. So a mixture problem is the kind of problem where you are given two different chemical solutions, and we want to combine them together to create a new one. So maybe you have a solution that's like 20% rubbing alcohol, and you have one that's 50%. And I want to combine the two together to create one that's 30. And I want to have exactly 10 gallons of it. So I want to know how much of each original solution do I have to mix to create the desired strength, 30% solution, and the desired volume. So this requires two equations. This turns into a system. Well, the first equation is just going to represent the total amount. So let's say you use X liters of solution 1, Y liters of solution 2, and you want to get 50. Well, in that case, it would be X plus Y equals 50. And if all you knew was the total amount that you wanted, let's say you want 50 liters, and they didn't care about the concentration, well, you could mix 10 of one and 40 of the other. Or you could mix an even amount of both, 25 and 25. But what narrows it down is they're usually going to tell you the concentration they want. 30%, 40%. So this is the second equation. There's 6 things in it, but each pair is very similar. Each term in this equation is a product. It's a concentration as a decimal times an amount, plus a concentration times the amount. The amount is usually your variable, like X and Y. So the concentration times the first solution amount, plus the concentration times the amount of the second solution, equals the concentration of the final solution times the total. So this is the final concentration.
Is concentration going to be in decimal or?
Yeah, the concentration has to be as a decimal.
Okay.
So if they said a 12% solution, we're looking for 0.12. All decimals. So let's look at a problem and see if we can solve it. Does everyone have the two equations? So we have two solutions, and we have as much as we need of each one. So we have 10% solution and a 25%. What we want to do first is decide how we're going to represent the amount of the first solution and the amount of the second solution. What variable do you think we should use to represent how much, I don't know what we're going to do, liters? How many liters we're going to use of solution A? What would be a good letter? Yeah? I would just use A because that's the name of the solution, so then we'll remember. So the amount here is A, and I would do the same thing here. The amount there is B. So we're going to use A liters of the 10% and B liters of the 25. When we mix them together, we want to end up with 15, and we want to get exactly a 12% solution. So it makes sense if we look at it, we're probably going to use more of solution A because the concentration of that solution is pretty close to what we want for the final answer. So we're going to use mostly A, and then we're going to pour in a little bit of B to bring the percentage up a little bit. So let's start with our equation for the total amount. Anyone think they know what my equation would be for the total amount? Yeah.
X plus 1 equals 15.
And what are we using for our variables?
A and B.
A and B. So A plus B equals 15. So there's your first equation. What I would probably do with this equation right now is solve it for either A or B. Doesn't matter which one, but you'll see why in a second. If we solve that for A, what does A equal?
15 divided by B.
What is it?
15 divided by B.
Minus.
Oh, no, I forgot this. We're in there.
So 15 minus B.
Yeah, I was, yeah.
Okay, keep that in mind. We'll come back to it. What's the concentration of my first solution? 0.1. Times how much of that solution am I going to use?
We don't need minus A, right?
15 minus B.
Well, we're going to use A of it, but A is how much? 15 minus B. And that's really A. So it's the concentration of the first solution times how much we use of the first solution, plus what's the concentration of my second solution? 0.25 times how much of my second solution? We're using B. And now, what's the concentration for the final? Like when I mix it together. And what is the total amount of solution that I want to have? 15. Now, by doing that step we did up above, we did the substitution in our head. Now we don't have to do the substitution at this step. We just did it right as we wrote the equation. If you didn't, you would now have to solve this equation for A or B and substitute it in. All right, let's multiply that up. 0.1 times 15, 1.5, minus 0.1b plus 0.25b. I'm going to need to know what that product is on the other side in a second. What's 0.12 times 15? 1.8. Let's combine like terms. What's 0.1 plus 0.25? It's not positive 0.1, negative 0.1. Sorry.
0.15.
0.15b equals how much?
0.3.
0.3. And divide. B equals, what's 0.3 divided by 0.15?
Oh. Yeah.
2. So we need 2 liters of the solution we called B. And how many liters?
13.
Yeah. Because we wanted a total of 15. Okay, so a little bit more advanced problem, still ending up being a linear type of equation, but you had to create the system, use substitution, and solve.
Wait, sorry, how do you get the 13?
15 minus 2.
Oh, you're just solving for the 15 minus 8.
Yeah, 15 minus 2 equals 8. Any question on solving linear type equations? Okay, last thing, quadratics. So, quadratic equations are of the form ax squared plus bx plus c equals 0. Again, a, b, and c can be any numbers you want. Those are the coefficients of your squared, linear, and your constant term. But a can't be 0. Because what would happen if you make a 0? It becomes linear. You wipe the quadratic term right out.
Okay.
So one way to solve a quadratic is to factor. So this isn't really intended to reteach you factoring. We'll go through an example. But that's something really you need to know how to do when you come across a quadratic. It's factoring. If I specifically ask you to solve something with factoring, then it will be something that is factored. Let's try this one. So 2x squared plus 5x minus 3. No matter what the problem is, what's the first thing you always write down when you're factoring? Yeah?
Your x.
Even before you write letters and numbers. Parentheses. When you're doing this kind of factoring, you want to put down 2 sets of parentheses. Now you figure out your first term in each. What's going to be my first term? In the left set of parentheses and then in the right.
That's the first term.
Yeah, first
You
term.
need x for both.
Well, if I put x for both and I multiply them together,
Oh, no, that's right. It's very equivalent. I was thinking for yourself.
one of them has to be a 2x. Because 2 is prime, we're lucky. There's only one way to do this. We know that's right. If this was a 12, well, now you've got to look at 4 and 3, 6 and 2, 12 and 1. You've got a lot of options now. Okay, so that's not bad. What about my signs down here? Both positive, both negative, or one of each?
I think it's going to be both negative.
So if we did a negative and a negative, and you multiply a negative times a negative, will you get negative? No. So what does that mean?
You're going to get one of each.
We need one of each. It does make a difference which one we put where. So we can just try negative, positive. If it doesn't work, we'll switch them. And 3 is prime. So what would be 2 numbers that multiply to give me 3? Let's check it. 2x squared plus 6 minus 1 is a plus 5. So this is factored correct. So what would we plug in to the first factor to when you set that equal to 0? What value of x would make that first factor 0? What is it? 1/2. Yep. And what would make the second factor 0? -3. You just set each one of them equal to 0 and solve. Now, factoring is fine, but it doesn't always work.
Oh, how did you find the two constants in either parentheses one more time?
So the constants are, you have to multiply them together to get the last number.
Oh, okay, thank you.
You're welcome. And since 3 is prime, I only had one way to do it. If this number was like 24 at the end, now you have to look at 1 and 24, 2 and 12, 3 and 8, 4 and 6. So then it starts to get kind of bad. Okay. Any other questions on that?
If it was something like 4 or like 16 that has like multiple, how do you know which one to do?
Try them all.
Like 4 and 4 and 2 and 8, like 16 and 1.
Yep.
Try them all.
Okay.
Just try them. If you get good at factoring, eventually you can kind of look at it and tell. Like that's how I knew to put the plus here and not here, because I did it in my head quickly, and I knew I wanted a bigger positive than I did negative. It's not always that easy to do in your head though. So sometimes it's just trial and error. What other method can you use if factoring didn't work? Yeah?
Quadratic equation.
The quadratic equation. So if factoring doesn't work, we have to use this formula that's like -b plus or minus square root of b squared minus 4ac all over 2a. That crazy thing. Well, where does that come from? All that formula. How many people know where it comes from? Alright, so let's take a look and see in a couple minutes if we can see how we get that formula. There's one other way you can solve a quadratic besides factoring and quadratic formula. We talked about it a little bit. It's a method a lot of people don't remember, but it involves adding, I call it like a magic number to both sides. Does anyone remember completing the square? Does anybody remember what was the very first thing you always had to do if you wanted to complete the square? You want to remember the first step? Yep.
Make both sides equal to 0. Or make one side 0.
We want to move something to the other side.
You want to move the coefficients that you said.
Move the what? The constant.
Yeah.
So that would be your first step. If a, b, and c were all numbers and you wanted to solve it by completing the square, you would put the constant on the other side. Okay. So we have a minus c. All right. Now, what did we say about the coefficient of the squared term? Anybody remember what that always had to be? 1. So what we'll do now, to force that to be a 1, well, you tell me, what could we do here, here, and there to make this just x squared? Yeah.
Divide by 8.
Divide everything by a. So divide by a, and a. So now we have, you're going to start to see this right-hand side look more and more like the quadratic formula. So we have a minus c over a right now. So now we have x squared plus bx equals negative c over a.
Wait, why is
Oh, I'm sorry.
why is it no longer b? Okay, alright.
Yes, that's very important. Now, this is the part where we complete the square. Completing the square has something to do with that. Does anybody remember the two things that you do to the thing in front of x? You do this, and then you do that. Yeah? Okay, so you take half of it. Well, that's half of it. You divide it by 2. And then what did you say to do? Square. So that's half of the middle term squared, which is b squared over 4a squared. Any question on? I can leave it like that. It doesn't matter. Eventually.
Is that the next step to do? Or is-
Yeah, I won't do it out like that, but eventually we're going to have to do it out on the other side. So now we're completing the square. So we're going to add a number to both sides, and it's half of the middle term squared. So b over 2a squared. And if you add it on the left, you have to add it on the right. b over 2a squared. If you want to do it out now, you can. You're going to have to do it.
Right, but how did you get B over 2? Okay, so it's just, you just haven't done it out yet. I see.
Yeah, I haven't done it out yet. Now, I don't really need to do it out on the left because the left-hand side at this point is going to factor. Remember, it always factors into something times itself. That's the whole point of completing the square. Like x plus 2, x plus 2, x minus 8, x minus 8. Well, does anybody see what the two things would be that this would factor into? Yep.
The first number is x.
And what would go right here? Yep.
Would be b over a.
Close. Yep.
B over 2a.
B over 2a. Because if you FOILed this out, I'm going to erase this but just to show you quick. If you FOILed that out, you will get back exactly what we started with. X squared. You get x times b over 2a and another x times b over 2a. So you have two of them. That essentially cancels out this 2 because you have 2 of the same thing. So the 2 is gone, and you have x b over a. The 2 is gone. And that's what we have right there. And then b over 2a times b over 2a is b over 2a to the second power. So that is correctly factored. Now on the right, what I want to do is kind of start putting this in the order you're used to. Let's write this term first and square it up. B squared over, what's 2a squared? Yeah?
4a squared.
Yep. Minus c over a. Now, I will come back to that left-hand side in a second. But anybody see what I could do next? I'll give you a hint. It's on the right-hand side, so let's keep this the same. What's the only thing I could really do on the right-hand side at this step? Yeah?
Square it.
We are going to do something with a square root in a little bit. But it's something just involving these two fractions. What's something you can do with two fractions? Oh, I'd like to do it, but I can't here for a certain reason. Yeah?
Make sure the denominators are the same.
Find a common denominator. Because if you want to combine them together into a single fraction, you can do that, but you need a common denominator. What would I multiply the bottom by to make that denominator the same as that one? What would I multiply by? 4a. And where else do I have to do it? In the top, look what you just got. Minus 4ac. Right, so quadratic formula a little bit, starting to come up. So now you have b squared minus 4ac over, now you have a common denominator of 4a squared. Now, someone already said the next step. What would the next step be to get x by itself? Square root both sides. So we're going to square root. And remember, when you square root a fraction, you do the top and you do the bottom separate, just like that. So now we have x plus b over 2a equals, well, you can't really do anything with the top. That's the square root of b squared minus 4ac over, what's the square root of 4? 2a. So now we have the square root of b squared minus 4ac over 2a.
Oh wait, that's not.
And what would be my last step to get rid of b over 2a? Subtract it. Minus b over 2a. And I'm just going to put it right here. So we have x equals negative b. Because it's a square root, we really need to do plus or minus the square root of b squared minus 4ac, and this denominator and this denominator are the same. So we can put it all over 2a. So in about, I don't know, it took maybe 3 or 4 minutes, we can see where the quadratic formula comes from. All the quadratic formula is a shortcut for completing the square.
That's crazy.
Every time you use quadratic formula, this is what you're really doing. You are completing the square. But it does all the completing the square for you without having to think about the steps.
So is this just for like general knowledge, or will we be left applying that?
We're going to apply that formula right now. We're going to use it.
But it's just showing that it's the same thing as the equation we're used to.
Yeah, this is how you prove the equation you're used to. This is how you prove where it comes from. Yep. All right. So here's your formula that you're used to. I think we mentioned this, but the part under the square root is called the discriminant. And to use it, you need to write your quadratic equation in a certain way that makes a, b, and c easy to see. Okay? So it has to be written in that form.
Sorry, what was the last thing you remember?
So to use the quadratic formula, you have to be able to identify a, b, and c. And a, b, and c can be identified if you set it equal to 0. And there's a, there's b, and there's c. Okay, got that one, and let's do this. Let's do example 7, because it's actually one more step. Example 6 already has it equal to 0 for you. Example 7 doesn't. So what would be your first step here to get this equal to 0? Yeah?
You just have to subtract 1 from both sides.
Subtract 1. And I would write it this way. That's descending order, highest exponent to lowest. So what is A in this case? B and C. So now we're going to solve that using quadratic formula. What are we really doing? We're really completing the square. It's just all being done for us with this magic negative b plus or minus all this stuff. All right, so negative b plus or minus the square root of b squared 4ac. Again, double check me here. I think that's right. negative 3 plus or minus. And we're going to have, well, first of all, what's negative 1 times negative 1? 1 times 4. So it's 9 minus 4 over negative 2. And 9 minus 4 gives me 5. Now, if it says solve, and it said, it was very vague, didn't say I needed a decimal, we can leave it just like that. That's the final answer. Okay, any question on that? So the last one we'll do, it's going to be a word problem similar to the one that's in the homework. We'll at least set the equation up. If we don't solve the whole thing, we can always go over it when we do homework. This is the last one.
Oh, yes.
So it says we have a rectangular piece of cardboard, and we're basically going to cut the corners out so we can fold the sides up to make like a little tray. We're going to fold it along the dotted lines. So we're going to cut a square that's 5 inches by 5 inches out of each corner. So each corner, 5 by 5. It says 5 inches over each corner. The rectangular piece of cardboard has a width and a length marked right here. When I say the width is the whole original piece of cardboard, and the length is the original length of the piece of cardboard before you cut the corners out. Length is not just the length of the tray after you fold the side. Just to be clear about that. Okay, so what do they want to know? Cardboard is folded along the dotted lines. All right, so here's an important piece of information. The length is twice the width. How would I write that as an equation? The length is twice the width, yeah?
L equals 2W.
Okay, I don't know how we're going to use that, but chances are we're going to get another equation with an L in it, and we're going to change L to 2W. Now it says the volume is 2,040 cubic inches after you fold the sides up and you make a tray. Find the dimensions of the original, I should be clear there, the original piece of cardboard.
Oh, yeah, before the corners were cut.
Yeah, with the original length and the original width. What shape is this when you fold the sides up? It's a 3D shape, yeah? It's a rectangular prism. And what's the formula for the volume of a rectangular prism? Yeah?
Length times height.
Okay, so length times width times height. So let's start with our...
Wait, if you wanted to solve this, couldn't you just find the volume of 5 by 5 and then multiply it by 4 and add that to the volume? Because isn't that the area that's missing on all the corners? A 5 by 5 square.
Well, we cut out a square, but the answer, or the number they gave us is a volume. A square is
Oh, I see. So you
area.
find like area, and then I see. Never mind.
So, well, I think there's one dimension we know here easily. What's the height of this tray? It's 5. When you fold the side up, it's going to have a height of 5. So that's easy. Now, let's think about the width. When we talk about the length, the width, and the height here, we're talking about the shape after we fold it. So this, yeah, I should be careful here. This length and width That's the length. That's the width. So in terms of our original length, if that's the original length, how much did we cut off the original length when we cut the corners out? We cut 10. So when we fold it and we make our shape, the tray is going to have a length of what it was originally, L, which, yes, is 2W. I'll get to that. The length of my final shape folded is the original piece of cardboard minus the 5 we cut off each side. Now, what's the width of my folded shape? W minus 10. Now, someone a second ago said, well, we know L is 2W. So really, this is 2W minus 10 times W minus 10 times 5. I should have done this down below. Any question on that? That's the length of my folded shape, the width of my folded shape, and the height of my folded shape. Now, if we wanted, what can you factor out of 2W minus 10? A 2. What's 2 times 5? So you're left with 10. And if you factor a 2 out of here, what's left?
5. Or negative 5.
Partially.
Oh, yeah, okay.
So you can make it W minus 5 if you pull the 2 out and then multiply it with the 5. And W minus 10. So there is a formula for your volume. There's a formula for the length, but we already used it, so we don't really need that again. And what did they say the volume was equal to?
2040.
2040. So 2040 equals 10 times W minus 5 times W minus 10. What could I do on both sides there? Divide by 10. So that gives me 204 equals. And then what would I do with this W minus 5 and W minus 10? It's already factored.
Oh, yeah, the reverse of factor.
Yes, FOIL.
Oh, that's it.
W squared minus 10 minus 5 plus 50. And basically, what kind of equation do we have there? It's not quite in the format yet, but it's a quadratic, which we want to get it equal to 0. And now just use quadratic formula. And that will give you the width of your original piece of cardboard. They wanted to know the dimensions. So you've got the width, double it, and that will be your length. Okay, so we actually went through more of it than I thought we would, but we're like 90% done the problem at this point.
Okay, wait, how would you find W and then you can just like explain it in words?
Get it equal to 0 and use the quadratic formula.
Oh, like the negative.
Yeah.
The negative. Yes.
Yeah. So minus 204 from both sides. And then use quadratic formula.
Okay.
It might even be, actually, this might even be factorable once you minus 204 from the other side. Actually, it is. It's factorable. You don't even use quadratic formula. But I would use quadratic formula because the numbers are big enough. I might not see how to factor it. All right, so the first thing we did, that was a break-even problem. So page 88, 35 to 39, that's a break-even point problem. And then page 96 is on solving linear and quadratic equations.